All right, assignment 19, 8.8, logistic growth functions. Your essential question, how do you evaluate, graph, and use logistic growth functions? So logistic growth functions have a certain equation that go with them, and it looks like this. C over 1 plus A times E to the negative RX. And if we graph it, I think this will make a little bit more sense to you. So I'm going to graph it using the quadrant 1 of the coordinate plane. So logistic functions take on this shape called a sigmoid. They basically look like an S. So it looks something like this, where at some point you have this point of inflection, which we'll call a point of maximum growth. We'll talk a little calculus right now. So you can see right here, if I were to draw like a straight line along this part of the graph, this is the steepest or the biggest slope of the graph, right? If I come down here and I draw a straight line, a tangent line, okay, it's going to be less steep than it was here. And same up here, to the point where it starts to even flatten out, so your rate of change is less up here, way less down here. So this is your point of maximum growth. This is where, for example, an infectious disease such as COVID-19, this is where it's infecting the most people at the quickest rate, okay? Up here is where it's starting to die off, okay? Down here is where it's just getting started, okay? So you have this point of maximum growth. That's what we would call an inflection point. Basically, the curve goes from being concave up to concave down. In this area here, let's see, we have an increasing growth rate. So, how can I do this? So I'll just put it here. No, I'll do it down here. How about this? So this area is an increasing growth rate. And this area up here is a decreasing growth rate. Now you're going to have two asymptotes. One of your asymptote is always at y equals 0. Oh, forgive me, this is my x, this is my y. And the other one is going to be where y equals c. So up here, y equals c, this is going to be a horizontal asymptote. So I'll just go ahead and I'll draw it as a dotted line up here. So this would be my y equals c. Okay, so basically these are exponential growth functions that don't increase without bound. So something happens where, you've got this really crazy increase happening, and then all of a sudden it starts to decrease. The growth rate slows down. So I like to use the example of like a bunch of rabbits on an island, right? So you start with some island that has no rabbits on it. You put 2 rabbits on the island. They just go into a frenzy and start reproducing, maximum reproduction here. They're eating all the vegetation that's on the island. And so it starts to slow down the reproduction rate because there's not enough food to support all the rabbits that are being reproduced. Another great example is COVID-19. So we started out with just a few people having the virus. It goes into this crazy exponential growth where we end up with people all over the planet with it. We start socially distancing ourselves, and so then the growth rate decreases until hopefully it's just going to flatten out, right? And then our number of cases will definitely decrease. Okay, so that's a great example of a logistic function. So they're used a lot to model real-life quantities whose growth level's off because the rate of change of growth changes. It basically starts to decrease. Okay? All right, so let's see. Let's talk about its characteristics. So you have horizontal lines at y equals 0, so we'll call those horizontal asymptotes. Oops. And at y equals c. Let's see, your y-intercept, or at time being 0, if we made the x-axis be time, like how many people initially had COVID-19 or when it originally started, your y-intercept you get by always plugging x in or 0 in for x. So if I plug 0 in for x, I'm going to have e to the 0 power, which is just 1. So your y-intercept is always at c over 1 plus a. Or you just plug 0 in for x. Okay, so I'm not even going to write that down, but it does have it as a bullet point in your book. I'm on page 518 if you wanted to follow along. Domain is going to be all real numbers. However, if we're talking about time being your x-axis, you probably wouldn't go back in time, right? You'd say, you know, starting from this day forward. Okay, so it makes a little bit more sense. But we can always say starting from this day, and if I want to look back 5 years, well, then that is negative time. The range goes between your two asymptotes. So you're always going to be in between 0 and c. And the graph is always increasing from left to right. If you want to find your point of inflection, so the point of inflection or the point of maximum growth, is going to be, basically you're going to take ln of a, oops, I didn't do that very well. Let me try that one more time. Make it a little bit bigger. So you're going to have ln of a over r, which is your rate, and then you're going to put c over 2. So this is the point, your x value you get from doing ln of a over r, and then your y value you get from doing c over 2. Okay, so those are just some characteristics of a logistic function, and now we're going to actually do a couple of these. They're going to involve graphing and solving. So let's see, why don't I start with this example where I don't need to use graph paper, and then I'll do another example where I do want to use graph paper. All right, so example 1, which is actually example 3 in your book, we're going to solve the logistic function 50 over 1 plus 10 times e to the negative 3x equals 40. Okay, so we're wondering, when is this thing going to be 40? So maybe, for example, this was a model modeling the growth of the COVID-19 virus in its early stages, and we're wondering, when are 40 people going to actually be infected? 2 ways to solve this. One is algebraically, and one is on your calculator. So I'm going to start with my calculator, and then we'll see if we can do the same thing algebraically. So let me grab my calculator here. So again, you just can use y1 and y2, right? So the first one, I'll just do 50 divided by, and I'm going to put my denominator in parentheses. I'm going to need e to the negative 3x. I encourage you to do this along with me, because if you don't, then you don't get practice doing it. Oh, I made that y2. I don't know why I was already on Y2. That's fine. I'll switch them around. So then my Y1 will be 40. And I'm going to make sure that my window goes up to 40, which right now it goes up to, oh, a lot. Let's go, how about 50? And let's see what that graph looks like. Okay, so I have my X values are way too much. I can shrink my X window maybe down to, let's go 20. Okay, so you can see your logistic growth function, which is growing pretty rapidly here, and then does end up flattening out, which is pretty nice. 50 is going to be my horizontal, my maximum horizontal axis, right? And then y equals 0 is going to be my other one. So I'll figure out where they intersect. So I know that they're intersecting at 1.2, we'll call that 1.23. Now let's see if we can figure that out algebraically. Okay, so that was using my graphing calculator. Now let's do that algebraically. So I'm going to basically take this. Now to me, this looks like a proportion, right? Two things set equal to each other, so I can cross multiply. Or you can just think about, hey, I got an x in my denominator. I got to get x alone, so I got to get it out of the denominator, so multiply both sides by this denominator. Okay, so basically our next step here looks like we get 40 times 1 plus 10 times e to the negative 3x equals 50. Okay, now solving for this, so I think what I'll do is I'll distribute that 40 because I need to get that x out of there, and I need it out of the parentheses. So I'm going to go, okay, this is 40 plus 400 e to the negative 3x, and that's going to equal 50. Now I'll subtract the 40 from both sides. So I get 400 e to the negative 3x equals 10. Divide both sides by that 400. So I get e to the negative 3x equals 1/40. Okay, and then the next thing, you have a couple options that you can do here, but if we took the ln of both sides, that would allow us to bring down that negative 3x. Okay, so that's what I'm going to do here. I'm going to go ahead and ln both sides. So I've got the ln of e to the negative 3x equals the ln of 1/40. Now this allows me to bring this down. So I've really got negative 3x ln of e equals ln of 1/40. ln of e is just 1, so that actually is gone, right? So we just have negative 3x. I'm out of room, so I'm going to come over here. So we have negative 3x equals the ln of 1/40. Divide both sides by negative 3. Put that into my calculator. So ln of, oops, that's e. ln of 1 divided by 40. And then divide that by negative 3. And we end up with, oh, look at that, 1.23. I'll put approximately. So if I wanted to know when 40 people were going to be affected, and I was given the logistic model for the COVID ID or COVID-19, I would know that, you know, and depending on what my X is it number of days? Is it number of hours? Who knows? But let's assume that it's days. My input here is days. So in 1.23 days, I'd have 40 people infected. Okay, moving on to example 2. This is on page 518 in your textbook. We're just going to graph this. So we're going to use everything that we know about finding like the point of inflection, finding our horizontal asymptotes, finding our y-intercept. And that should be enough for us to do this graph. Okay, so first of all, I know that I have horizontal asymptotes. at, okay, well, one of them is always going to be at y equals 0. And the other one is going to be where C is, right? So this is my C up here. So the other one is when y equals 6. Now to find my y-intercept, basically that's where x equals 0. So my y-intercept would then be 6 over 1 plus 2, because if I plug 0 in for x here, that's just going to be 2 times 1. This whole thing here goes to 1. So that's going to be 6 over 3, or 2. So I know that 0, 2 is a point on this graph. And the last thing I'm going to do is I'm going to find that point of maximum growth, or that point of, so let me bullet these, point of inflection. So point of max growth, or we'll call that inflection, where the concavity changes. It goes from concave up to concave down. And the way that you do that is you basically use that little formula that I gave you on the last page, which was ln of A over R, and that'll give you your x value, and then for your y value, you go C divided by 2. Okay, so let's work on that. So this is going to be, let's see, my A is 2, so it's ln of 2 over my rate, which is 0.5. The negative is part of the formula. Okay, so when I originally gave you the formula on your previous page of notes, the negative was part of the R, right? So, sorry, it was being multiplied by the R. So the R is that, basically the absolute value. It needs to be positive. Okay, and then C is 6 divided by 2. Okay, so going into my graphing calculator, I need that for the ln of 2. And I'll divide that by half. So I get about 1.386. 3. So that's where my point of inflection is happening. Okay. And now we can just kind of put this all together and do a pretty simple graph. I don't need any negative x values. I mean, the graph continues in the negative direction, but it's not so important that you have a whole bunch of negative x values, and you definitely don't need any negative y values because your y-axis is a horizontal asymptote. All right, so 1, 2, 3, 4, 5, 6. We've got our y-intercept at 2. And we've got our point of inflection at 1.38. So I don't know, about there, 3. I'm going to label this. So this is 2, 3, 4, 5. Okay, so that's interesting. It basically, the fastest rate of growth is happening quite quickly, right? So it's going to look something like, and you can definitely get more points, but it's definitely your y-axis, or sorry, your x-axis is an asymptote. So it's going along that, coming up through this, but then it starts to level out. Oops, I didn't do a very good job of that. Let me try that one more time. Because you don't want your y-intercept to look like your point of inflection. You want your point of inflection to look like your point of inflection. So let's try that again. So it comes up, and then it starts to level out there. So maybe something like that. It's important that your graph shows that it goes from concave up and then concave down at your point of inflection. So this right here is 1.3863, and 0, 2 is pretty obvious. Okay, we're going to do one more example together, and that's example 4 out of your textbook. So we're going to use a logistic model to, and really, I mean, it would be kind of cool to really do the COVID-19 bacteria or virus, but we'll do a colony of bacteria here that it's growing in a petri dish. But you can basically imagine any type of virus or bacteria spreading in such a way. All right, so I'm going to call this example 3, even though in your book it's example 4. So your textbook, I'm on page 519. Your textbook talks about a colony of bacteria, B. dendroides, is growing in a petri dish, and the colony's area, A, in square centimeters, can be modeled by this, right? It's eventually going to grow to a maximum area. It's not going to be able to grow anymore because the petri dish is only so big. That would be the same like with the COVID-19. I guess it could only grow to how many people are in the United States, like 327 million people. Once everybody had it, then it basically couldn't grow anymore. Hopefully that's not going to be the scenario here. Okay, so it's modeled. This is the model that's actually modeling the bacteria. You better believe that there are scientists out there right now that have models for this for the COVID-19 virus. Now, T is the elapsed time in days, and we're going to graph the function and describe what it tells you about the growth of the bacteria colony. Okay, so we're going to do another graph here. We're going to use A equals 49.9 over 1 plus 134 times E to the negative 1.96T. Okay, so this means that I have a horizontal asymptote at about 50, or 49.9. And then my other horizontal asymptote is going to be, again, at y equals 0. So I'll go ahead and I'll write that. Horizontal asymptote at y equals 0 and y equals 49.9. We're going to have the y-intercept. That's going to be where we have e to the 0, so it's going to be 49.9 divided by, well, 135. And then we're going to have our maximum growth, or our point of inflection, just abbreviating here. And that's basically going to be the ln of 134 over our rate, which is 1.96. And then we're going to take C, which is 49.9, and divide that by 2. So that gives us our point of inflection. Okay, let me do a little bit of math here to get these numbers. So the y-intercept, I'm going to do 49.9, divide that by 135. So this y-intercept is going to be 0, and then it's a very small number, so how about 0.37? And then the point of inflection, let's do a little bit of math there with my calculator. ln of 134 divided by 1.96. Okay, it's going to be 2.4. Well, let's just go 2.5. And then 49.9 divided by 2 gives me 24.95. Okay, so now graphing that, I know I need to go all the way up to 50. So maybe I'll go by tens. Oh, that wasn't a very straight line. That's okay. And in this case, I know that this is the area in centimeters squared. And I know that this is the time in days. It's good to label your axes so that you have some way of understanding what's happening. If we were modeling the COVID-19 virus, we would say, all right, this is the number of people infected. And then this would be time in days, hours, however you wanted to do it. I would probably do it in days because that's usually how the information is coming in. Okay, so graphing this, let's see, I've got a horizontal asymptote up at 50. So if I go maybe 10, 20, 30, 40, 50. Could I do this any other way if I have 10, 15, 20? Oh, okay, I'll go by fives. So I know that I have a horizontal asymptote somewhere really darn close to 50. And I'm going to show that by actually labeling it y equals 49.9. Okay, I've got a y-intercept at 0,0.37, so it's like right here. Very, very, very low. Almost to 0, really. I've got a point of inflection at 2.5. So maybe I'll just go, for days, I'll go 1, 2, 3, 4, 5. Good enough. So at 2.5, I'm about right here. And that's my point of inflection. And I can plug in other points so I can figure out what's happening afterwards. I'm just going to go ahead and use my asymptotes to help me. So I know that I should be going close to the y-axis, coming up, and then this is going to be my point of inflection. So something like that. And I'll go ahead and I'll label my point of inflection as 2.5, 24.95. And this is not so obvious either, so I'm going to go ahead and label my y-intercept. Okay.